We've discussed 4 physical quantities in electrostatics so far. We've talked about electric forces, we've talked about electric fields, and these are point charges. We talked about electric potential, and we've talked about electrostatic potential energy. There's something I want to point out about all of these quantities. First off, for forces and electrostatic potential energy, you can only calculate a force between charges, or a force of 2, 3, 4 charges on another charge. Same thing with potential energy. You can only find the potential energy between 2 charges, or a series of charges taken 2 at a time. On the other hand, for electric fields and electric potential, you can only find those quantities at a point in space. So there's no way you can calculate what the electric field is on a charge. It has to be the electric field at a point in space due to a charge or a distribution of charges. And the same thing is true for electric potential. So one way to keep these quantities straight is to realize that forces and energy have to be between 2 charges. Fields and potential are calculated at points in space where there are no charges. So I just wanted to make sure that was clear before we moved on. We had a nice expression for electric potential in terms of electric field. And of course, the integral is the line integral, and of course the dot product indicates that we're turning these 2 vectors, a displacement and an electric field, into a scalar. And so you might ask the question, well, if I can get an electric potential from an electric field, can I get an electric field from an electric potential? And since I had to integrate to get from E to V, is there some way I can take a derivative and get from V to E? And the answer is yes, but it's not a simple derivative. For example, suppose you have a potential that is a function of x, y, and z. And I want to calculate the electric field from that potential. A simple derivative won't work if I have 3 dimensions. Now, if the potential is only a function of x, very, very clearly, I would think that I could go dv dx to get my electric field, and that would be correct. But because typically a potential can be a function of 3 variables, we have to use a special mathematical operation called a gradient. And so what that is first off, we can say that the electric field is minus the gradient of the potential. The gradient, this upside down triangle, is defined as an operator that operates on a scalar function and converts it to a vector. By itself, it's meaningless. It has to operate on something. In this case, we're going to have a gradient operate on a potential, and that will enable us to determine an electric field. So, for example, this is probably the easiest way to do it. Let's do a numerical example. Suppose I have a potential that has the following function. 4x squared z plus 3y plus 2y z squared. And I want to find E at some point in space. Let's find it at x equals 1, y equals 1, z equals 1. So what I have to do then is to take a series of partial derivatives in order to obtain the components of the electric field. So when I want to find the component of the x component or I component of the electric field, I have to take the partial derivative of v with respect to x. That means we treat z and y as constants. And if I do that, in fact, take the negative partial, that will be equal to and multiply by the unit vector I. So if I take the partial with respect to x, that will give me 8x, negative sign in the I direction. If I take the partial, 8xz, if I take the partial, negative partial of v with respect to y and multiply by j, that will give me a minus 3 for the second term and a minus 2z squared, again holding z and x constant. And that will all be in the j direction. And then if I want to find the partial with respect to z in the k direction, I hold x and y constant, so I get minus 4x squared in the first term, and I get minus 4yz in the second term, all multiplying k. So put it all together, my electric field then is minus 8xzi minus 3 plus 2z squared j, distributing out the minus sign, minus 4x squared plus 4yzk. And if I put in the values 1, 1, 1 for x, y, and z, I'll get an electric field that looks like minus 8i minus 5j minus 8k. So it's a very simple way to obtain an electric field from an electric potential. We use the gradient operator. Those who take Cal 3 will get a much better understanding. They do a much more thorough and rigorous treatment of the gradient operator and directional derivatives and so on and so forth. We're just going to use the actual operation for our purposes. I'd like to look at some other applications of electric potential before I move into continuous charge distributions. Let's look at the electric potential due to a dipole. So suppose I have a dipole along the x-axis, and I have a minus q here and a plus q here. And let's say that they're separated by a distance a. And I'm looking at some point P on the x-axis. I want to find the electric potential at point P. Well, the electric potential is just going to be 1 over 4 pi epsilon naught sum qi over r pi sum over I, which I can write as 1 over 4 pi epsilon naught q over x minus a plus q over x minus q over x plus a. If I can get a common denominator, and I'll get qa over 2 pi epsilon naught x squared minus a squared. And so that's the electric potential due to an electric dipole at some distance along the axis. suppose we ask the question, suppose X is much, much greater than A. If that's the case, notice what I can do. I can let A go to 0 in the denominator, and I'll get QA over 2 pi epsilon naught times x squared. Let's see if that checks with what we did earlier in calculating electric field. Let's look at what would be the far field equation for an electric field for a dipole for x much, much greater than A. Well, all I have to do then is take the negative derivative of v with respect to x. That should be equal to the electric field. If I do that, guess what? I get QA divided by pi epsilon naught x cubed, which is exactly the far field expression we came up with for the electric field of a dipole. It has a 1 over x cubed dependence. So no surprise. I'd like to turn to a somewhat interesting topic, and that is, let's look at the electric potential due to a continuous charge distribution. With several examples of that. First one I'd like to do is, let's look at the potential due to a uniformly charged ring at some point, a distance x from the center of the ring. Let's say the ring has a radius A. Write this according to here's some point on the ring. I'd be some distance r, and I can write this as theta if I like. If I want to find a point along the axis, the potential for a point along the axis, V is 1 over 4 pi epsilon naught integral dq over r. If the ring has a total charge q, notice r, I can write r as the square root of x squared plus a squared. But these guys are constants. X and a aren't changing in this problem. So my potential can be 1 over 4 pi epsilon naught square root x squared plus a squared times the integral of dq, which is just q. So it will be q over 4 pi epsilon naught square root x squared plus a squared. Just like when we did the electric field due to the uniformly charged ring, we didn't actually have to do an integral. In this case, we don't either. Now, along the x-axis, E can only have an x component, so suppose I want to find, will I get the answer that I got back when I calculated the electric field? Well, one way to find out, E is minus the gradient of V. In this case, it's going to be equal to minus dV dx. And it's along the x-axis. Sure enough, if I take the derivative, what do I get? I get qx divided by 4 pi epsilon naught x squared plus a squared to the 3 halves. So it's exactly what we got back earlier when we did the electric field due to a charged ring. What's the potential at the center of the ring? Well, at the center of the ring, we found in 2 chapters ago that the electric field was 0. That must mean that the derivative of the potential with respect to x is 0. That means the potential must be a constant at the center. And in fact, it's either a max or a min. It turns out the potential at the center of the ring is equal to Q over 4 pi epsilon naught times A. We can build on this with a little bit more interesting problem. Let's do the potential for a uniformly charged disk by taking a series of rings, concentric rings, and forming a disk. So we're going to break this giant disk into rings of charge, because we already know the answer for a field of one ring. All we're going to do is add up the fields or integrate for all of the rings. Let's say that the entire disk has a radius capital R. If I look at one particular ring, I know that the area of the ring at some, let's say it's some distance little r, the area of this ring would be equal to 2 pi r dr, where dr is the thickness of the ring. I can use the answer I got before. The potential for one ring can be written as Q over 4 pi epsilon naught square root x squared plus, we'll call it little r squared for a ring with a particular radius little r. I can say that the area of the ring is 2 pi r dr. Therefore, I can write dq, because what I have to do, if this is the charge of one ring, I'm going to write dq as sigma dA, or 2 pi sigma r dr. And if I want to find the potential, I have to sum over all the rings, from r equals 0 to r equals capital R. What does that mean? I'm going to take pi times sigma over 4 pi epsilon naught, integral from 0 to r, and I have 2 r dr divided by the square root of r squared plus x squared. I'm going to integrate over the radius of the entire disk. This is the radius of one ring, and it's going to vary from the center all the way to the edge. So little r is going to go from 0 to r. X is just a constant. That's the distance out here where I'm trying to find the electric potential, call it point P, find the electric potential at that point. This integral is fairly simple. It's a u du type integral, where I can write u is r squared plus x squared, and then du is 2r dr, which I have in the numerator. So I can do this integral fairly simply. When I do that, I'm going to get v is equal to 2 pi sigma over 4 pi epsilon naught, square root of r squared plus x squared from 0 to capital R, which will give me sigma over 2 epsilon naught x squared plus capital R squared, the 1/2 minus x. By the way, we can check that answer, because before we had determined the electric field for this particular configuration at point P. If I take the gradient of V, the negative gradient of V, I will get the electric field. When I do that, I'm going to get sigma over 2 epsilon naught, 1 minus x over the square root of x squared plus r squared, which is exactly what I got when I did it several videos ago. So that's a nice example where we determine the potential due to a ring fairly simply and then just integrate over a series of rings to get the potential of a disk at an axial point away from the disk. Suppose I have a finite line of charge and it extends from the origin, let's say, to some length L. And let's say I want to find the potential along the y-axis at some distance A, at point P. So I want to find it at some point on the y-axis due to this uniformly charged rod. So let's say that it's got a length L, it's got a total charge Q, and it has a uniform charge density, linear charge density lambda. So what I need to do is I'm going to need to make my expression dq over 4 pi epsilon naught r, and I'm going to evaluate, well, put the evaluation in later. I can replace dq by, in this case, I want to integrate over the length of the rod, and so to do that, I have to do the following. I have to look at every point on this rod as some distance r, which is a squared plus x squared, square root, from point P. I can write this then, I'm going to write dq as lambda dx, 4 pi epsilon naught, and r I'm going to write as the square root of x squared plus a squared, evaluated from 0 to L. That will get me my potential. And this is x squared plus a squared to the 1/2. This is not as easy an integral as it may appear to be. I have to be a little bit judicious in what I do. What I would recommend doing is saying, the way to think about it is, let's use this angle theta, and let's let theta sweep from here to here so that we cover the whole rod. That being the case, I'm going to say, let's let x equal a tan theta. I'm going to let dx equal a secant squared theta d theta. That says v then is equal to lambda over 4 pi epsilon naught integral a secant squared theta d theta divided by, this would be a squared tan squared theta plus a squared to the 1/2. Tan squared plus 1 is secant squared, so I can do the following. I get secant squared on the secant squared on the bottom A's cancel. Secant squared to the 1/2 is just the secant of theta. So now I have to integrate secant of theta d theta. I'm putting 0 to L, but that's not really the limits. We're going to have to go back to x's to do that. The trick in solving a secant theta equation is to multiply top and bottom by secant theta plus tan theta. It's a great integral trick. I remember when we did this integral, it was I was teaching my son's class, and my son and his friends all wanted us to do the integral out rather than looking it up in a table, and from that moment on, I was always one to do the integrals out. I didn't use integral tables after that, at least for integrals such as this. If I do that, I'm going to get, this is very nice, I get tan theta secant theta plus secant squared theta divided by secant theta plus tan theta, integral, and the mess outside. Notice this is the derivative of the secant, this is the derivative of the tangent, so this is like saying the integral of dy over y, which of course is just a log of y, or the log of secant theta plus tan theta. Put that all together, I have v equals lambda over 4 pi epsilon naught, and I get log secant theta plus tan theta. If I look at my triangle, that's theta, that's A, that's L, and that is R. So what I have immediately is that